Hello everyone, this is Athota Rathan Babu, working as an assistant professor in the Department of Aeronautical Engineering, and I'm going to deal with the course Computational Aerodynamics. And today's topic we'll see continuity equation in differential form. Okay, so let's have a small recap. So we had seen these things already in the previous lectures itself. So how CFD has formed, then after what are the steps in the CFD, continuity. So we are actually trying to derive this equation. So this continuity equation we had seen it is in this is differential form. So first it is derived in integral form. Then the integral form equation it is applied for the control volume which is fixed in space. So how we will derive the continuity equation in the differential form for the control volume, the fluid element approach we will see. So these are the examples of external flow, internal flow, and so we have two popular methods: Eulerian and Lagrangian method. To derive our continuity equation, we will see Eulerian method. So Lagrangian approach is about tracking of each and every fluid particle with respect to time. So we are not going to do that one because the density of the fluid which is present on the Earth's surface is very like it's 1.2 to 3 kg per meter cube, so it is significant amount. So that's why we don't consider the Lagrangian approach. So we'll be taking the Euler approach to derive the continuity equation. So we'll be deriving continuity equation. So this is the domain actually whatever we see. So this domain is divided with the help of mesh into subdomains. So you can see cells which are called the subdomains. Okay, so basically this cell is called subdomain, so this cell is subdomain, so you have so many number of cells. So at these cells we will apply our governing equations and we will see so how they are changing. So you can see non-uniform grid along x-axis, so this is what we have, non-uniform grid along y-axis. So basically we use non-uniform grid along y-axis because like we need to capture the boundary layer. We'll see once why we need to give more spacing for the y axis. So we'll just see here. So basically like let's take you have a mesh. So this is mesh. Okay, so basically here there are the points called grid points. So the intersection of x and y lines will rise to grid points or the node points. Okay, so here let us consider this is a boundary. So this is what we have. So this basically these are called the boundary points. Okay, B. So here these are called boundary points. So these points which are present here, those are internal or the node points. Okay, so here what we are doing is like so we need to calculate what should be the minimum distance of first grid point actually. So this one is the first grid point. So this one is the first grid point above the wall. So if we consider this is wall, so what should be this distance? Okay, so what should be this? So this is called y plus. If you take like wall along x-axis and so this is the boundary point and this is the node. So basically this distance, let's say this is called x plus. Similarly, you have z plus. Okay, so you need to calculate what is the x plus and what is y plus and what is z plus for the grid actually first. So how do we get that one is like, so first we need to calculate what is the bond layer thickness along these axes. Okay, so if there is any bond layer formation along these axes, so you need to see what is the thickness of the boundary layer. So based on the thickness of the boundary layer, you will be taking the spacing. So the meaning of y plus is, so the location, so what is the distance of first grid point which is located above the wall. So this is the meaning of y plus here, and x plus is nothing but what is the first grid point which is located along the x-axis, similarly along z-axis here. So now, so let's consider if we have flow over flat plate. Okay, let us take an example. let's take an example. So you have, let's say this is flat plate. Okay, so let's take, these are the boundaries which we have. So this is called wall, which is flat plate. Okay, and this is the boundary which is inlet, and this is the boundary which is outlet. This is inlet and this is outlet. Okay, and this is called far field. Fine. So here the inlet is a place where the flow is entering with certain velocity. Okay, outlet is the place where flow is leaving with certain velocity out. Far field is a region where you have undisturbed air. So because of presence of this wall, so if you have any undisturbed place, so that is called the far field, where the wall effect on the air will not have any significance. Okay, so now we need to calculate what is y plus. So we don't have x plus here. Why? Because the bond layer formation here you have actually the y plus, sorry, along y axis if it is 2D, and so if we have a 3D, so let's say domain, so the bond layer is like 3D. Okay, and anyway, like we need to calculate what is x plus and what is y plus and what is z plus for a full scale domain. When you're going for 2D domain, so it is better for us to calculate y plus, and x plus is also fine, but we will focus majorly on y plus. Okay, so now basically we need to see what is the Reynolds number. So let's say if you have a velocity v inlet is equal to some 2 meter per second. Okay, reference length is let's say 1 meter. Okay, density is 1.225 kg per meter cube. So let's say you have these things. So we have a parameter called Reynolds number, so which is nothing but rho v l by mu. So this is the Reynolds number. So this parameter actually is defined. Why? Because so basically we are discussing about thickness of the boundary layer. So here we have thickness of the boundary layer, which is inversely proportional to under root of Reynolds number. So Reynolds number is nothing but rho v l by mu. So this is what we have, and we are seeing that we have this as a domain. So we have wall here, and we have inlet, and we have outlet, and we have far field. Okay, so we were discussing about the x plus and the y plus since it is 2D. Okay, so this distance is, let's say this is x plus, and distance this is y plus. So basically, as we had seen, like let's take velocity is equal to 2 meter per second, reference velocity. So reference length as 1 meter, and density which is 1.225 kg per meter cube, and mu we have the value of 1.8 into like 10 power minus 5, so depends. Okay, so here if you substitute those things, you'll get the value of Reynolds number. So from that you will be able to calculate the thickness of the bond layer. So once we get, let's say it is something like 0.001 meters, so your the distance of the first grid point should be placed below 0.001 meters. So let's say it should be like 0.00009, something like that. So then only you will be able to capture the bond layer clearly. So if not, if you are using, let's say, the distance of the grid point as 0.005, so then what happens? So if you have this as mesh, your bond layer will form inside, but this is not captured in the mesh, and you will be not able to see. You are just keeping it. Okay, in CFD. So these things has to be taken care. Fine. So this is the importance of the y plus and x plus and z plus if you take. So we had seen the substantial derivative. So basically, so when a fluid particle is starting from position 1 and is reaching position 2, how the fluid flow properties, let's say density, pressure, temperature, velocity. So these things are varying with respect to time at different instants, and with respect to space, how it is moving. Okay, so it is combination, like you have local derivative and you have convective derivative. Fine. So we have seen that the density at a second point, so rho 2 will be equal to rho 1 plus dou rho by dou x into x2 minus x1 plus dou rho by dou y into y2 minus y1 plus dou rho by dou z into z2 minus z1 plus dou rho by dou t into t2 minus t1. So this is what we have. So these are the terms which we had seen for the Taylor series of expansion. So when we rearrange these terms, so what happens? So this becomes rho 2 minus rho 1, which will be equal to d rho by dx into x2 minus x1 plus d rho by dy into y2 minus y1 plus d rho by dz into z2 minus z1 plus d rho by dou t, so t2 minus t1. So this is what we had. So we will multiply and divide by t2 minus t1 for every term. So here you have t2 minus t1. So here also you have t2 minus t1. So t2 minus t1. So this will be equal to u. This is v velocity. This is w velocity. Here this is cancelled. Okay. So x2 by, so u velocity is nothing but the average quantity x2 minus x1 divided by, so t2 minus t1. So v equal to y2 minus y1 divided by t2 minus t1. So w equal to we have z2 minus z1 divided by t2 minus t1. So this is what we have. Okay. So u velocity, v velocity, w velocity. So here this quantity rho 2 minus rho 1 divided by t2 minus t1, so which is capital D rho by dt. Fine. So this one is capital D rho by dt, which is called material derivative or total derivative or substantial derivative. So is written, d rho by dt is written as u into, so dou rho by dou x plus v into dou rho by dou y plus w into dou rho by dou z plus dou rho by dou t. So this is the substantial derivative of the density. Okay, so this is what we have. So when a fluid particle, when it is going from station 1 to station 2, so with respect to time, how it is varying, you can see. So instantaneous, the local derivative term. So then the remaining terms which we have, these are convective derivative terms. So let's clearly see here. So d rho by dt will be equal to, so dou rho by dou t plus next v dot delta, so v bar delta and rho. So basically this is what we have for the substantial derivative. So here we know that v bar is nothing but ui cap plus vj cap plus wk cap. So this is what we have, comma gradient is equal to dou by dou x of I cap plus dou by dou y of j cap plus dou by dou z of k cap. So if you do dot product of these two, then you will be getting dou u by dou x, dou u by dou y, dou w by dou z into, like, you have the density term. Fine. So we have written short form. So this is the instantaneous local derivative. So at this instant, what is happening for the density? Okay. So with respect to position, like with respect to time, how it is changing, and when it is moving from point 1 to point 2, so because of the convection, let's say the fluid motion, so how the density is changing. So convective acceleration term and the local acceleration term. So simple, if you want to write a general form of substantial derivative, so d by dt will be equal to, so dou by dou t plus, so v bar dot delta. So whatever the variable that you have here, it will come here, it will come here. So this is what we have for the substantial derivative. So we have seen different approaches for the fluid. So already we have seen the finite control volume which is fixed in space, and finite control volume which is moving with the fluid, and here you have infinitesimal fluid element. Okay, so which is fixed in space, and infinitesimal fluid element which is moving with the flow. Okay, so these two, like if you observe, so here you can see already we had seen this derivation. So we had seen the integral form of governing equation in conservative form. So basically, when a control volume is fixed in space, we derive a governing equation in a conservative form, and that too, when you do or when you derive equations for the control volume, then you'll get the integral form of governing equations. Okay. Now, if we derive governing equations for a control volume which is fixed or moving with the space, we will derive integral form of non-conservative form of governing equations. So this is the difference which we have. So this is fixed in space, and this is moving with the flow. Okay. So here, so the second one you can see. So basically what is happening is d by dt of this is entire mass is equal to 0. So when this control volume is moving with the flow, so in general, like you have d by dt of m is equal to 0. So the mass is constant. Okay. So always the same number of fluid particles will be present in this control volume which is moving with the flow. So therefore the mass is not changing. But but here mass is equal to what? Density into volume. So the density may come down and volume may increase, so that this mass is getting compensated. So the shape of the control volume is not fixed. If it is moving with the fluid, it can change. So let's say this is this position. At this instant, let's say this is this one. Here you can see the volume decrease, the density should increase. So next instant, the control volume, let's say it might go like this. Okay. So this is what we have. Okay. So basically the mass is constant and the volume and density can change. Okay, this is what we have. So let's see here now what we can see or how we can derive this differential form, and let's recap this integral form of governing equation. Okay, so here you can see the continuity equation, so which is written in if it is moving with the flow, it is non-conservative form. So let's see first conservative form. Okay, so now first let's recap the integral form one. So if you take this control volume, so the flow is going like this. Okay, so the control surface, this is fixed in space. So the rate of amount of mass that is decreasing in the control volume will be equal to the flux that is leaving through the control surface. Okay, so here you can see so dou by dou t. So basically this is rate of decrease. So negative symbol is decrease inside the control volume. So this is volume of mass. So density to volume. So these terms will contribute to the rate of decrease of mass inside the control volume. So this term will be equal to the flux or the flux which is leaving to the control surface. So we have a surface integral. So rho v dot delta s. This is what we have. So this is the generic continuity equation. General. Okay, in general. So this is what the continuity equation that we have. So we have to put all these things in, let's say, volume integral. So what we will do? We will change the surface integral to volume integral. So how we will do? So we will keep this as a volume integral. So this will be del dot. This will be rho v. Okay. So, and if you see total equation, so that would be, so dou by dou t volume integral, so which you have rho dou v is equal to 0. So this is what we have. Okay, so this is the continuity equation which is derived in the integral form of equation. Fine. So we can change this one to the differential form. How? If we take the integral cancel out like common, and if we take that one out, so you will be able to get the differential form equation. So first we can change from one form of governing equation to another form of governing equation. So what happens at the end? At the end, you will able to write the differential form. So let's see here. So basically, what we have is this one: volume integral of dou by dou t rho dv plus volume integral del dot rho v volume integral is equal to 0. So if you take out this integral form, then you have dou by dou t rho plus del dot rho v is equal to 0. So this is what we have. So this is the differential form of equation, so which is converted from integral to this thing. Okay, this is derived in conservative form, that too for a control volume which is fixed in space. Already I told you for the moving space, so we have this volume integral. Basically it is d by dt of rho dv. So as I told you, the mass is constant. So as it is moving with the flow, the mass is constant. So density and volume can change. So the meaning is, so when the control volume is moving with the flow, the shape can change. It's not like shape is fixed. Okay. Now, so we have the fluid element approach. Till now we had seen the control volume approach, which is fixed in space and moving with the space. Now we will see fluid element approach. So here you can see, so the basic thing what we have, let's take this as x-axis and this as y-axis and this one as z-axis. Okay, so here the distance along x-axis is, let's say, delta x, or let's say dx. Here this is dy, here it is dz. So the coordinate axis is in this way. So you can see this is dx and this is, let's say, this is here it is taken as dz and here it is taken as dy. Okay, so this is what we have. So when the flow is entering in all sides, let's say it is entering along x-axis, leaving y-axis, entering along y-axis, leaving y-axis, entering the z-axis, leaving z-axis. So this is what we have. So when it is entering, so already I told you, like, we have this mass flow rate. So mass flow rate is nothing but basically d by dt of density into volume. So this is what we have. So next, d by dt of density, what is volume? Area into length. So basically this becomes area into velocity. So mass flow rate is nothing but density, area into velocity. Okay, so basically how velocity has come? So this one we have written as rho a dl by dt. So this term is written as velocity. Okay, so we have rho av. Fine. So this velocity, this type of formulation we apply for a fluid element. So you can see rho u along x-axis. So if you see along x-axis, you have So you have rho u. So basically you have density into velocity. Area is, what is the face area here? So this is y and this is z. So then it becomes dy and dz. Okay, which is entering. So when it is leaving, what happens? So it has traveled x plus delta x distance. So when it is traveling x plus delta x distance, so what happens? So with respect to initial, so which is rho u plus dou x of rho u into dx. So this is what we have. The flow which is leaving when it is traveled with a distance of delta x. So when it is traveled a distance of delta x, so this is the term which we have. This is the density into velocity term. Into, so what is the phase we have? So dy dz. Okay, so this is what we have along x-axis. So if you take the net along x-axis, what happens? Rho u into dy dz. Okay, so we have rho u plus dou by dou x of rho u into dx into dy dy dz minus rho u into dy dz. So here what happens? This term and this term is getting cancelled. So what is the remaining term we have? So we have the remaining term, which is dou by dou x of rho u into dx dy dz. So this is coming along x-axis. Okay. Similarly, what we have along y-axis? So we have rho v into, so what is the phase here? So let's say this is y-axis, dx and dz. So that would be dx and dz. So which is entering along this phase, and during leaving, what happens? So this is at y, and at y plus delta y. So what happens? This would be rho v plus dou by dou y of rho v into dy into dx dz. So this is what we have. So this is at y plus delta y, and this is at y. So the net what happens? So rho v plus dou by dou y of rho v into dy dx dz minus rho v into dx dz. So here you can see this is also getting cancelled. So the remaining term what we have is like dou by rho v into dx dy dz. Similarly, what we have? Similarly, you will have the term which is having with z direction. Okay. Similarly, you have the term with z direction. Finally, what we have is like we have the term dou by dou x of rho u into dx dy dz is dv volume plus dou by dou x of rho v into dv, which is volume, plus dou by dou z of rho w into dz is equal to, sorry, dv is equal to 0, let's say. So this is what we have. So for an incompressible flow, let's say, if we take the volume integral common, so the final equation that would come for incompressible flow is, so dou by dou x of rho u plus dou by dou y of rho v plus dou by dou z of rho w equal to 0. So since it is incompressible, you take density terms out. So dou by dou x of u plus dou by dou y of v plus dou by dou z of w is equal to 0. So this is what we have for a differential form of equation for an incompressible flow. Okay. So if it is unsteady flow, then you will have the density term, which is varying with respect to time, and if the flow is incompressible, even dou rho by dou t term will be equal to 0. So this is what we have. Basically, this is the flow which is leaving, whatever I'm saying. But the other terminology, whatever we have, is like the flux, the rate of decrease which is inside the fluid element will be same, like dou by minus dou by t rho into dv. So this is what we have. So till now, this thing is the flow which is leaving through the phases. So this is whatever the flow that is changing inside the fluid element. So if we add these two together, then that becomes dou by dou t of rho. So this one and this one I'm saying. So because of these phases, we have this equation, dou by dou x of rho u plus dou by dou y of rho v plus dou by dou z of rho w. So is equal to 0. So basically, so this is due to convective term. And here the rate of decrease of mass inside the fluid element is written as like dou by dou t of rho to dv. So here we have into dv everywhere. So if we add these together, we'll get a continuity equation which is in differential form. So what is that? Plus So this is what we have. Okay, so here if you're talking about total derivative term, you'll have the total derivative term. So this is what we have. If you expand so these things, so you will be able to write. So what is it? So this can be written as u, so rho delta u plus u del rho. So this term is expanded in this form. Okay, so when you take this one and this one, this would become substantial derivative. So therefore what happens? So that become capital d rho by dt plus what we have, rho v dot del is equal to 0. So this is the final form of the equation. Okay, so basically we can change from one form of equation to other form equation, but the physics of the flow as should not be changed. Okay, it is very important to see that the physics of the flow is governed, and the thing is that if you compare here for the all the things, okay, so here we had already initially seen. So what is the continuity equation with respect to fixed control volume? So continuity equation which is with moving control volume. So if it is not moving, it is conservative form. If it is moving, it is non-conservative form. But the governing equations which you have here should not change the physics of the flow problem. So that should be valid actually. Okay, so it should not deviate, or it should not like what do you say, have give the false information regarding the physics of the fluid. So whether it is a fixed in control volume or whether it is in a moving with control volume in space, so these two should have the identical things. Okay, now in the fluid element approach, what we had seen, so we had directly applied the differential form of equation directly. So what flow which is entering through phases, different phases, we have seen the flux, and we have added whatever the molecules that are decreasing inside the fluid element. So that is directly written as minus dou rho by dou t into volume. So this is what we have. So you can see this is differential form of governing equation, and we had changed. So here again I will explain it. So this thing so is written as dou rho by dou t. So this del dot rho v, the vector operation is changed actually. So what is written? It is written as rho del dot u plus u dot delta into rho. So basically combination of this one and this one will give rise to substantial derivative. So which is nothing but capital D rho by dt plus rho del dot v bar is equal to 0. So basically this is the derivation for control volume which is moving with the flow. So if it is incompressible flow, what happens? So again what we have, so you have del dot rho equal to 0. So whatever it is based on the assumption, so you will get the physics of the fluid which is same, and it should not deviate. Okay, so by learning this, so what we do is like we have now the governing inside the governing equation. So we have du by dx term plus dv by dy term plus dw by dz term is equal to 0. Let's say this is for incompressible 3D flow. So if it is 2D, what we have? Only these two terms. What are these things? So dou u by dou x plus dou v by dou y is equal to 0. So this is what we have. So now what finite difference formulation represents? So this first derivative is replaced in this form. This is what? Along x-axis. So how it is written? We'll see. So u of I plus 1 minus u of I divided by delta x plus v of j plus 1 minus v of j divided by delta y is equal to 0. Okay, so this is what we have. So when you take common delta x, delta y, so if you multiply these things, like, so you will have a linear term here. So what we have done, we have replaced this partial derivative term in terms of discretized form. So this is our main agenda in CFD. So in the further classes also we'll be seeing so how the momentum equation is derived, then how it is discretized actually. So here you can see the first order derivative, second order derivative. So already we have discussed. So basically what is order of accuracy. So here you can see this f of x plus delta x, f of x. So already we have discussed. So here f is nothing but u. So x is nothing but I. So plus delta x is nothing but 1. So is equal to, so u f of x, which is nothing but u of I comma j. So u of I plus 1 comma j is equal to u of I comma j. And here you have dou f by dou x. What is dou f by x? So dou u by dou x, delta x. Plus you have dou square f by dou x square. Therefore what happens? Dou square u by dou x square, delta x square by 2 factorial. Plus so on. We are till n. So now what we are doing? We are trying to get this term from Taylor series of expansion. Why? Because in continuity equation we have du by dx term. So dou u by dou x term is there. So how we are writing? We are writing it as, so dou u by dou x into delta x is equal to u of I plus 1 minus u of I comma j divided, here this thing, minus dou square u by dou x square, delta x square divided by 2 factorial plus so on. Now if we divide this one here, like what happens? So here you have delta x. So this one you can remove here. Now here you can divide by delta x. So if we consider only this term, then it is called the first order accuracy in space. Okay. So you can discretize these terms in the continuity equation. We will replace partial derivative term with respect to discretized form using Taylor series of expansion in different forms of accuracy. So if you additionally consider this term, if you are able to perform this dou square u by dou x square term in u of I plus 1 and u of I comma j and this form, so then you will get a second order accurate continuity equation. So why I am telling first order? Because so here the power is delta x. So here you can see the first leading error term is delta x. So since it is space, it is first order accurate in space. If it is time, then it is first order accurate in time. Okay. So in the next session we'll be seeing so how the continuity equation, we have seen the continuity equation, how the momentum equation is derived, and how do we discretize that momentum equation. So in a momentum equation, basically it is derived with force is equal to mass into acceleration. So basically on the fluid you have different forces. You have surface force and here you have body force, and this acceleration of the fluid particle is written in substantial derivative term, which is dou u by dou t. So this is why we had first initially seen substantial derivative. So this is expanded in this form. So dou by dou t of u plus u into del dot v into del dot u. So this is written in this form here. This a is replaced in this form. And you know m, density into volume. So these forces, F, surface forces, body force. So surface forces are nothing but the pressure and viscous or the shear we say. The body forces are gravity, some other thing. We'll see the detailed information and we'll see the small derivation, like how the continuity equation is developed and how many forms of equations are there. Then what is the physical significance of continuity equation and what is the physical significance of momentum equation in CFD. So we'll see in detail. Okay. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.